Hey everyone, it's Mr. Canfield. So we're going to be doing the second part of chapter 34 today. This is going to focus on what's called the second fundamental theorem of calculus. So here's the deal. Instead of taking the integral of this from 1 to a number, we're taking it from 1 to x. So let's see what happens. So if we do this, well, this integral is pretty straightforward. I know I said I'm not going to do calculator integrals. This is it. Don't worry. This is just for this one right now. I don't know what words came out of my mouth. What I meant to say was, I know I said we're only going to do calculator integrals. I might have said the exact opposite. Okay, so our integral of this is really straightforward, right? It's going to be t cubed over 3 minus, that's going to be 4t squared over 2. So we're going to be dividing by 2, so it's going to be minus 2t squared plus t. And we're going to evaluate this from 1 to x, right? So pretty straightforward. We're going to wind up getting, let's see, x cubed over 3 minus 2x squared plus x minus, and we'll plug in 1. So it's what, 1/3 minus 2 plus 1. So it's -1, -2/3. Okay, so, right, we can, if we want to, we could very easily, instead of going from number to number, go from number to a letter. It's definitely possible. So what happens if we take the derivative of this now? So 5b says, take the derivative of that, right? Well, didn't we say that when I do this, this actually turns into this thing over here? So that is that is that. Well, hey, what's the derivative of this? Actually, let me back up. Let me be really, really clear here. This integral had t as its index. It was with respect to t that we took this integral. X was a different variable. So we ended up with a different variable in there. The derivative that we're being asked for is not the derivative of this variable, but the derivative of that variable up there, one of our bounds. That's going to be really important with this theorem. Essentially, this is a special trig theorem that's awesome. Because check it out. What's the derivative of this? Let's see. Well, x cubed over 3 turns into 3x squared over 3 minus 4x plus 1. 2/3 goes away. Wait, hold on a second. The 3's cancel out. We get x squared minus 4x plus 1. So, in case what we just did is lost on you, we started out, we had an integral. We took the integral. Then we took the derivative, and we ended up with what we started with, except the variable changed. So that took me 4 minutes to say, hey, if you take the derivative, if you have x as one of the bounds and you take the derivative of it, you just plug the x in, you're done. And there should be some element of that where that feels stupid. Like, why? What's the point? Yes, totally, I hear you, great. But that worked. This is called the second fundamental theorem of calculus. And stated, mathematically speaking, we can say if f is continuous on an open interval containing a, then for every x in the interval, the derivative with respect to said x from a to x, or the derivative of the integral from a to x of our function is equal to f of that value x. And chain rule applies here. That's the main thing. So we'll look at some examples. So this first one here, if it goes from a number to x, it necessarily follows this and does this exactly. Therefore, you don't need to do any of that. 6a says take the derivative with respect to x from 1 to x of t squared minus 1 dt. The reason these are different variables is if these were the same variable, we would have a very strange situation where we're not trying to say that this and this are the same. I really think we could even change it. Like we could say this is DDA from 1 to A, and these could be x's. Don't get hung up on this being t and that being x. They're just different. But this is literally, so this is one of those where I would say the concept is really high and the execution of this is basic. Basic. So B. All right, now we start getting into weirdness. Just kidding. It's the same thing. You just plug in the x and you're done. It's great. No work. We are going to use this to do some trippy stuff later, but for now, this is literally as simple as it. Done. That's it. C and D kind of turn it on its head a little bit, so let's make sure that we make sense out of these. So this time it's not just x cosine x, because the x wasn't on the top, the x was on the bottom. But if you remember rules about integrals, one of our rules is that if we reverse the bounds, throw a negative out front. So this is the same as 3 to x. Right? So if I throw the negative out front, now it's the same as 3 to x, so I just gotta throw a negative out front there and we're done. And then the last one, wait, does he really only go that far? I would like to do one, I guess he doesn't have any with double variable. So if we had double variables, we would do like the first, like plug in the first variable minus plug in the second variable. But anyway, so D says ddx, not ddt. Pi over 2 to x squared. Okay, so this is the only one that we really got to make sure we're careful. So if you think about that process, right? We first took the integral, we got a thing, we plugged in the x, right? And then we took the derivative of that thing. So if you can imagine with me, we're going to take the integral of this, we're going to get something, and there's going to be x's in our answer, minus some e with numbers, like who cares? So there's going to be x stuff, but every x that we plug in is going to be an x squared. When we take that derivative at the end, it is going to look like e to the square root of x squared. But when I took the derivative, there's going to wind up being an x squared somewhere in there that I take the derivative of, and so I'm going to wind up multiplying my answer by the derivative of the inside. So this is one of the tricky situations where when if it's not just x, if it's something else, don't forget to do chain rule and multiply by the derivative of the inside. So you could almost think about it like, oh, well, the derivative just means plop that in, and then since that's not x, multiply by the derivative of that. I mean, and with the x's we did too, because, you know, I guess we could say we multiplied this by the derivative of x. It was just 1. This one was just 1, and this one was just 1. So that's it. That's the second fundamental theorem of calculus. Places where this shows up are, we'll have AP questions where we'll see things like f of x is equal to the integral from 1 to x of f of t dt, and you'll have some kind of graph like this. So let's see. Okay, so just pretend that those line up perfectly, and we'll say that, let's see. Here's 1, here's 2, here's 3, 4, and 5, okay? So you'll see things like this, and then we're able to ask questions like this. What is f prime of 4? And we have to be careful. And if we think about this, it actually turns out to be very, very simple. F prime of 4. Well, this is f, right? Oh, sorry. We'll say that this is... We'll say this curve here is f of t. So there's some other function we're going to call f of x, and it's equal to the integral of this function. Oh my goodness. They'll usually use different letters. There. Okay. So we'll call this guy g of x, and we're saying f of x is the integral of this guy. There. I got my labels wrong. So this is some graph, we'll call it g, and we'll say, hey, so f of x is the integral of our graph here. So what's f prime of 4? F prime of 4 means take this and take the derivative of it and plug in 4. Oh, wait. What's the derivative of this? G of x. Plug in 4. Go over here, what's g of 4? G of 4 is 2. So this is a classic AP question, where if it said f prime of 5, you take the derivative of the integral, you just drop the x in and you're done. It's just g of 5, so it's, oh, look at the graph, it's 1. But then, you also get things like this. Hey, what's f double prime of 3? So think about that. F double prime. Well, f double prime means we take the derivative of this, and then we take the derivative of what we get, and then we plug in 3. Well, let's think about that. The derivative of this is g of x, right? And then we're going to take the derivative of that, and we're going to get g prime of x. And then we're going to stuff in the 3. Well, hey, g prime of 3. Remember, what's the slope of the tangent line when x is 3? So go to your curve, go to 3. What's the slope of the tangent line? there would be something that says, hey, this is definitely a relative maximum. Or like there would, but it looks like it's flat. And yeah, so there's lots more that we can see with this, but that's a good start. We are going to spend the rest of the day today doing problems where the where the calculations turn out to be really basic, really easy, but finding out what calculations they're asking us to do, what we're supposed to do, that's the puzzle. So, yeah, hope that was helpful. Bye.